it's my pleasure to have here this bunch of people who work on computational game theory in Sage Maths, which is a project I happen to be affiliated with, and I do some work in Sage Maths as well. So they are specifically aiming in getting as much game theory algorithms and implemented and available online for free using your favorite computer language called Python. So as the names are all there, so this is Vincent Knight from Cardiff University. I will introduce.
Great. Yeah, well, thank you very much for having us, and thank you for coming. I realize it's a busy time and whatnot. So, Dima very kindly invited us here. Dima and I are actually both mentoring Sabina, who's a Google Summer of Code student who's working on other things. And Hannah and James are undergraduates at Cardiff University, first year and second year, respectively, and they're also working on this big project. We don't have any slides as such. We thought we'd use Sage itself to present Sage. So what we're using here is called sagemath.cloud, which is a web system that, cloud.sagemath, that allows anyone to just use Sage. Why isn't that going away? Let's see if that goes. There it goes. So I'm just in a browser, allows anyone to just use Sage, Python, R, whatever language, more or less whatever language you want on there. So this is just a
hospital, I think.
Yes. And Sage Math is a project with a interesting mission statement, which is to provide a free open source alternative to Mathematica, Maple, etc. I don't know if you're all familiar with Sage Math.
Yes.
No? Okay. If you're interested, there's this website that gives a lot more information. The project started in 2005, and it's 10 years old now, and going very strongly. And it's used in teaching as well as research. All students at the School of Mathematics at Cardiff learn Sage and various other places. What we're going to talk to you about today is some code that's now in Sage that allows you to solve game theoretic problems. So I'm not going to speak for too long, and I'm going to let every person who's built the code describe it. So here's a very simple game. It's one of the games that's taught in Game Theory 101, so to speak, and it's called the Battle of the Sexes. So if Bob and Celine wanted to do something one evening, and ideally they'd like to do it together, but Celine prefers to watch sports, and Bob prefers to watch a comedy. If Bob chooses sports and Celine chooses sports, then you see their utility here is 2 and 3, so they both get a relatively high utility, but Celine gets a bit more because Celine's seeing what she prefers. If, however, Bob chooses sports and Celine chooses a comedy, then they're at least seeing what they prefer, although I think that's slightly the wrong way around. But they're not getting anywhere near as high as here. If, however, they both see comedy, then they're not getting a high utility. But if they're both seeing comedy and sports, they're getting a utility of 0 both. Okay, so hopefully a relatively straightforward game. What you see here is a green line between these two nodes. And that's meant to represent that Celine doesn't know what Bob is choosing when Celine makes her choice. And that's called an information set. Hannah's going to talk about that a bit more later on. So that just means that they can't coordinate their behavior. Celine doesn't know what Bob's choosing. Celine has as much information in that node as she has in that node. Now, prior to our work in, so then right here, this is another way of representing the game. Just a bit low, perhaps. Let me tighten that up to the middle. Here are just two matrices that represent the same game. So that would be the utilities to Bob, that would be utilities to Celine, and we allow Celine to control the columns and Bob to control the rows, and the numbers should be the same. So this is called an extensive form game representation. It's actually that picture is actually being drawn using code that's in Sage, and this is what's called normal form representation. It's just with two matrices. And before our work in Sage, the way to handle, well, one of the ways to solve games and manage games is with Gambit, and Gambit's another open source project that Sabine has actually had a lot of involvement with prior to this project. And Gambit's great. We're very much, throughout the work that we're doing in Sage, we try and make sure that what you can do in Gambit, you can do in Sage, and you can use Gambit seamlessly with Sage. And I'll just show you a little bit of Gambit. So this is the interface on cloud.sagemath, and so now I'm opening an IPython notebook. That's interesting.
Are you offline?
I shouldn't be. I think it's probably when I restarted the project earlier. There it is. So I don't know how familiar you are with Python, but Gambit has a nice Python API, and so I can import Gambit, and then this is some Gambit syntax to write the game. So I say it's okay, it's a 2x2 game, and then I go through every cell, say which player, and I give them their utilities. And once I've done that, we see that this is the representation of the game, which has all our information there. And then here we have a solver, and that returns Nash equilibria, well, the pure Nash equilibria of this game, so I'm only going in a pure solver. Something I should have mentioned, and maybe we'll demo it before the end, is that on cloud.sagemath, there's lots of stuff that allows you to do things in a very cloud way. So you could have someone writing on this at the same time as you, and vice versa. It's also just a full Unix machine. So I'm now going to write the output of this game to a file. And if I go to my files and I go to game.nfg, we see that I've written that file to a file. And this is where I'll hand over, well, just about to hand over to James, because now back in Sage, so I'm back in the Sage worksheet here, I can still import Gambit and use Gambit in the exact same way, and we'll have a Gambit game object. And this was something we were very keen on, that we still get that same object. And now what I'll do is I'll hand over to James, who will discuss what you can do with all these things.
So one thing we were very careful with was that we wanted you to be able to use anything you've done with Gambit in Sage, so any code you'd written already. So as Vince has just shown, we now have this Gambit game object, and we can create a normal form game within Sage from that. The normal form game class is code that I wrote last summer, and is a bespoke implementation of normal form games within Sage. Currently only available for 2 players, but that's something that's being worked on as we speak, the ability to solve for n player games. So if we evaluate this, we can see that any game in Sage has a Sage representation, a dictionary of the strategies being played, and then a list of the payoffs for each player. And we can then obtain a list of the equilibria for that, the Nash equilibria for that game. It's just a list of tuples for each player. We then also have our own way of building a game, so you don't have to go via Gambit. Just as Vince showed before, we can represent the game as 2 matrices where one player is the row player and the other player is the column player, and we can pass these matrices to the normal form game and build the game in that way. And then we show that, it's exactly, we get the same representation as before. And then whenever if we ask to show the game, we get the LaTeX out, and again it renders, so we can always see the payoff matrices.
Get this LaTeX and paste it into your paper.
Yeah, you can. So if I get rid of that show, there is a. Ooh,
I've still got my thing, so press I.
So we can have the LaTeX code, and then show just automatically renders that LaTeX code for us. So then if we solve it again, the obtain Nash, we get this list of tuples. But we have more than one algorithm to obtain these Nash equilibria. This is a good way of showing Sage's inbuilt help function if at any point you add a question mark to the end of a command. We can have a look at all of the documentation and all of the source code for the function. So here we go. One of our arguments is an algorithm argument. At the moment we have an LRS, LCP, and enumeration. There are also many others being worked on as we speak as well. That's all in development. I'll just get rid of that quick because it takes a lot of space. So yeah, thank you. Don't know why that wasn't already there. So enumeration is something that I wrote again last summer, bespoke in Sage. So this will work out of the box. Any current version of Sage, if you go on Sage, cloud.sagemath right now, you can create a normal form game and solve it with enumeration. Enumeration is also the default if nothing else is installed. But we also have LRS and LCP available to us. LRS uses a standalone C library, which has to be installed. If you're messing around with any of the polytope stuff in Sage, there's also a lot of LRS work there. And then LCP is something that we've got from Gambit. So again, if you've got Gambit installed, you can use Gambit's LCP solver. Again, that's written in C. But as you can see, classic. There appears to be a line hidden in there. I don't know how. There we go. So you can see they're all giving us the same equilibria. Some are the fact that some come as floats, some as rationals is just the individual package and how they work. One thing we noticed was that these algorithms didn't always give the same number of equilibria. They might leave some out. And so we had a look into that, and we discovered it was because these particular instances, the games were degenerate. This is another good example of some of the functionality within Sage. If I do tab completion here, we built a catalogue of normal form games, games that are used a lot in literature or teaching, simple examples. And we now have a catalogue, so you can these are all here under the tab completion. So if I use those, here we have rock, paper, scissors, lizard, Spock, and then rock, paper, scissors. So I evaluate these. Our top the top two matrices are for rock, paper, scissors, lizard, Spock, which is an extension of the classic rock, paper, scissors. If any of you have watched Big Bang Theory, that's where this was made famous. But we can see that if the row player plays his third strategy, the column player has two best responses, his first strategy and his last strategy. So this game is an example of a degenerate game. And so this summer I've been working on a function to test that fact. We can see that the first example, x, which is rock, paper, scissors, lizard, Spock, comes back true, and rock, paper, scissors comes back false. Jabin is now going to talk about some of the algorithms he's been implementing.
So one of the most popular algorithms on computation of the Nash equilibrium is the Lanka-Hausen algorithm. And the way it works is it works by pivoting on a pair of best response polytopes. One of the polytopes for the best responses of the row pair and one for the best response of the second. And it starts from a Nash equilibrium and it always ends at a Nash equilibrium. And the way you start is you just say what is the missing label. So for instance, if we start from the artificial equilibrium, which is usually the starting point, and we say, okay, missing label will be 1, we then end up going to the blue pointer from the first pivot. We now gain a new label, which will be 4. And then we decide, oh, we've got 2 4s. So we go to a point without 4, so we go to 5, and we check, and we've now picked up 1. So that is now the Nash equilibrium. If you repeat the same process with 4, you end up at the same point. And if you repeat this process for the other labels, you end up finding the red and the blue pair of points as the Nash equilibrium. Okay, I didn't show the payoff entries, but I was going to show them later on. But for instance, in this game, if you look at it, whenever the row player plays his pure strategy, his first pure strategy, the best response of the column player would be to play 4. If the row player plays 2, column player's best response is 5. If he plays 3, so based on this, you can plot, if you have the any probability factor, you can plot it on this, find the exact coordinates it is on the simplex, and you can say, okay, where if it's on this point, then 4 is the best response for the column player, for instance. Likewise for the row player. So, using this, if we apply this to the previous game, which is the rock, paper, scissors, and for instance, we start with, we can decide starts with the pure strategy 5, so with label 5, and we end up finding the Nash equilibrium where everything is mixed. However, this game has a unique Nash, so no matter which label we start from 1, no matter which label we start from, we always end up at the same Nash equilibrium. And we can also try to find all Nash equilibrium. Oh, sorry, mistake. And if we try to find all Nash equilibrium, the first one which we get is the artificial equilibrium, which is the starting point. And the second one is just an equilibrium which contains the unique Nash in the game. So if we look at, this is then the payoff matrix. So in this, the matrix A right there gives us the payoff matrix. The matrix game AB gives us the game which I showed you in the previous diagram. And in this, if we then try to find all Nash equilibrium, the when you start from the artificial equilibrium, you then first find a set of equilibrium which have a positive index. And this are the red and the blue labels which I showed earlier. And starting from those ones, from those equilibria, if we then start with the other labels, we then are able to find this, the new equilibrium, this, the third one. And if you look at this, each equilibrium has a property called labels. And that shows that starting from with label 1, we get to the positive equilibrium of 0. So the very first positive equilibrium. Starting with label 2, get to the second, and so on. And similar for the positive equilibrium. And this label, the relation between labels are unidirectional. So on directional sides. So starting from 0, from equilibrium 1, would also lead you back to the same equilibrium where it came from. And we can then try to show this using a bipartite graph and plot it. And we can see the relation between all the different equilibria. Next, what I'm working on is, currently what I'm working on is on the n-player representation of n-player games. So first off, to create an n-player game, you just create a regular normal form game without passing in the payoff entries. And then what you say is you just add the number of players you want, and you can then start adding, similar to the Gambit's syntax, for each of the pure strategy profiles, you can specify the payoff of each player, like the first 3 lines. Or you can either pass it with each of the payoff entries as a single list. That way you can just sort of avoid repeating lines of code. And by doing that, that gives us a regular representation. And this representation can also be converted into a Gambit instance, which is what we do for most of the for all the solvers which we currently have implemented. So the solvers which we have implemented are basically converting these games into a Gambit game and passing it to the Gambit solver. And we have all the Gambit solvers currently implemented. So we've got support enumeration. We just solved a system of polynomial equations to find the Nash equilibrium in the games. We also have all the other solvers, which include global Newton method, as well as some of the other methods there. So we've got iterated polymatrix, logits, simplical division method. Yeah. Moving on from that, the thing that is that depends on the result produced by Gambit. So for some of the solvers, the results are in fractions. For some of the solvers, the results are in floats.
So fraction is what is it a rational number?
Yeah, it's a rational number. Yeah.
It's actually 0, 1.
Yeah, and these are using Python fractions. Yeah.
Python 2. Go away.
I don't know. It's in a sub-library, isn't it?
Yeah, it's in a sub-library of its own. They've got fractions. They've got another one called decimals, which is.
So you somehow don't want.
No, this is currently the output that's Gambit spitting out. So
Yeah. So
yeah.
You don't want to, or if you will, change it into something more.
We could change it into a Gambit representation, but into the stage representation. Sorry, but yeah, at the moment, this is what we've been able to do. Another thing to note is that not all games, games can be solved by most of the solvers, with the exception of support enumeration. The remaining n-player solvers aren't guaranteed to terminate and find a Nash equilibrium. So, for instance, in this game, all the payoffs are zeros. Any mixed strategy any mixed strategy profile is a Nash equilibrium. However, passing this into solvers like the global Newton method, we just end up with nothing. And solvers like the iterated polar matrix, we just end up with it running infinitely and never actually terminating. So yeah, let me just stop that. So we do end up with that, and you have to forcefully terminate it. Otherwise, it will just keep running and never actually find one. Okay, and at this point, I'm going to pass over to
So extensive form games, which some of you may know as trees, are, you could say, very visual ways of representing games. So if you remember the tree that we would demonstrate at the very beginning with Bob and Celine, I will show you a way of building this now. This is one of the ways we can build it using classes we built in Sage. So here we have the code for it. Player, so we start by creating the players. So we've created Bob and Celine. Then we create the leaves, which is where we put the output. So we have this class EFG leaf, and within it we need to put what player has what payoff. So for this specifically, if we're looking at here, player 1, which is Bob, will get 2. And I'll show you what this looks like in a minute. And then we build our nodes. So within the nodes, it's also another separate class which has actions taking to either nodes or leaves. So to show again, this is taking, if player 2, sorry, I should have demonstrated, you also put in the node name and which player will be at that node. So player 2, so Celine, will take the action sports to leaf 3. So it might seem a bit confusing, but when you see it visually, it might make a bit more sense. So then you just simply build the tree, the extensive form game, by putting in extensive form game and then which node you want to build the tree with. We built it so you could put in node 2 or node 3, but right now we just want node 1. So if I just run these 2 cells to actually build the tree, and then if you just call the game, it will give you the underlying data tree graph, which which just shows you the relationships between the nodes, which is mostly built for building the actual tree plot, which I'll show you. This code. Sorry, I'm not used to Macs. So this is what the code above does, and you can see we built the tree here. It's Sage has a lot of graphical interface, and you can build plots of all sorts as you've seen before. And this is just something we've built so you can build an extensive form tree. Other things we've done. So we have another graph, which I will run and then explain what it is. So this is the information set graph, which is specifically a directional graph. So if I
just put 2 fingers on the mouse,
yeah,
and move them upward.
Yeah, it's just a lot more sensitive than I was thinking it was. So this is showing relationships between information sets. So the labels here are the nodes within the information set. So we have, so as we've seen before, I should have explained this again. This is slightly different from the tree at the beginning because there's no line here. This simply means that Celine knows that Bob has picked comedy and Celine knows that Bob has picked sports. So this is what this is showing. So these are in two separate information sets. We can change this by setting an information set. So those two nodes were node 2 and node 3. So we use the code set information set. We run that, and then if we plot the graph and plot the information set graph, okay, firstly we see this tree with the line now through it. We can see this has changed, the information set, although it's slightly too big for the screen. But all you'll see down here is the tree root node, and you'll see, now you see that these two are in the same information set. We've also implemented converting to and from Gambit, which is very important because we need to, because we've implemented a solver which uses Gambit. So if I show you this, it's just as slightly different because we're showing different equilibria. So I'll explain piece by piece here. If I can select, sadly I cannot select, but basically these are lists with different equilibria, and within those lists are lists for the nodes of individual players. So basically, if you go through one by one, you can see at tree root, for the action comedy, whatever player that is will not pick comedy, and then for the action sports, they will pick sports. And sometimes this is not like a whole number, it can be, so here, whoever picks comedy is a chance of 0.75. So then I'll show you then reading Gambit into it. So as I showed you a way of building it from the classes, this is a way of building it with a Gambit game. So you saw the NFG file earlier. An EFG file is very specific for extensive form games with Gambit. So if I input that, then I put that. So if I load that game, this is a Gambit game, then this, I'm using that Gambit game to create a Sage game, and then I'm just going to plot it to show what it looks like. So here we see it's pretty much identical. Everything is pretty much the same, even the information set. Only difference is this is fractions, which we've explained before. It's just the way Gambit reads things. And yeah, and now I'll pass back to Vince to conclude.
Thanks. So just to finish up a couple of details. The first being, you've seen these extensive form games and these normal form games. Another undergraduate student in Cardiff that's just started is building something that goes between them. So that's Reese, and he's building something that goes between the extensive form games and normal form games, so that you can go between them. So we have 4 open tickets, which is how the review process is done in Sage. So they're solvers for constant sum games that Turbina put up a while back. And there's going to be about 2 more over the next couple of days, couple of weeks, whenever they are. And James and I thought of something else that we need to include. So that's how the development process goes. And you can see that a lot of what's there is stuff that you've been shown today. So it's relatively brand new. We'd like to thank a couple of people and things. First of all, Summer of Code for letting Turbina have the ability to do this. Codima is a project.
It is an PSRC funded project for computational discrete maths, which is mainly with Santander's to develop Gap, which is a part of Sage in some sense. So they were kind to let us use some of this money here.
Thank you, Matt, and then thank you to people, Travis and Carl, who've been very, very helpful in getting a lot of tickets reviewed and a lot of help. And obviously, thanking Dima as well. And if anyone would like to get in touch with this little group of people that we are, we have a Gitter room, which is just a chat room that anyone can go on and drop us a line. And obviously, this is also on its own GitHub page as well. And then just a final couple of words about Cloud Sage Math. If I go right up to the top here, where there's some code, if I wrote something like that and I pressed enter and I couldn't understand why it wasn't working, then James, who's on his laptop, could just fix that, which is again nice. And I use cloud.sagemath for cloud.sagemath for a lot of my teaching. It's also got a LaTeX editor, which is really nice, helping students learn LaTeX without any of the installation process. And William Stein, who's the main guy behind cloud.sagemath, is working on what he already has implemented, and he's changing a course management system as well. So cloud.sagemath from a teaching point of view is a really nice tool, and I thought it'd be worth mentioning that. But overall, hopefully what we've shown and you've appreciated is that we've got a fair bit of game theoretic code written up. Anyone could kind of jump online and solve games fairly easier, and we're constantly trying to improve what we've got there and build more. So, and it's mainly thanks to these great students. So yeah, thank you very much.
I understand that as the department is planning to teach more games, so maybe this might be a useful tool.
I think from our point of view, I know James and I, we met someone who wanted to use some of the game theoretic stuff. We got extremely excited about that. So if anyone else wants to use it, or indeed in teaching or anything, if we or I can help in any way, we'd be delighted.
Effort of installing this thing on your computer is essentially zero.
Yes.
As opposed to effort of installing Gambit and using Gambit on your computer is quite an adventure.
Exactly. There is no installation process. You just sign up on cloud.sagemath, and even if you didn't want to use Sage, you wouldn't hurt our feelings. You can still open an IPython notebook and you can use Gambit straight there. And terminals as well. Yeah, this is just a machine. So there's a terminal. I can open up whatever I want. It says. Thank you for asking that. That wasn't a plant. I'm trying to remember off the top of my head what it's called. We have a matching game implemented, which you can't read the doc string apparently. Okay. So we have a matching game implemented. James, can you move? Oh, let me just grab it from here. Some code generated.
This is another great part of these Sage docs, is that all the tests are designed so that you can just copy and paste them straight into the Sage cell and they work straight away.
Because you have this.
Yeah.
There is a way to tell.
Yeah, there is.
More editing.
Now we have a matching game, and then is it?
Just do that.
So we can add reviewers, add suitors, and we can solve the game, and that returns a matching. And then if I do m.plot, we can see the matching. We also have a very basic characteristic game functionality implemented, so for Shapley value calculations as well for cooperative games. So those are the two things that we didn't feel fitted in as well with the original thing. It was great that you asked that, so you could show it off. So thank you very much. Anything else we could answer? But yeah, thank you for coming. Realize that you're busy, so thank you. No? Great. Thank you very much.
any questions? Well, we are all here tomorrow as well.
Yeah.
Feel free.
Any requests?
We will